Good evening, students. Today, let's move to next theorem. Suppose f is bounded on closed interval AB and f has finitely many points of discontinuity and alpha is continuous at every point at which f is discontinuous, then f belongs to R of alpha. That is, f is Riemann-Stieltjes integrable. So the given points are f is bounded on closed interval AB and f is discontinuous on only a finite number of points. Okay, and alpha is continuous at those points. Okay, so this is the given data and we need to prove that f belongs to R of alpha or f is Riemann-Stieltjes integrable. Okay, so here let's move on to proof. Let x1 dash, x2 dash, etc. up to xp dash be finite points where f is discontinuous. So they have given f has finitely many points of discontinuity. So we are assuming let these be the finite points where f is discontinuous. And also they have given alpha is continuous at every point at which f is discontinuous. So alpha is continuous at each of these points. Okay, and here I have taken the closed interval a comma b. So in this interval a comma b, f is discontinuous at these points x1 dash, x2 dash, etc. up to xp dash. So f is discontinuous at finitely many points. Okay, so these are finite. Okay, and also given f is bounded on closed interval AB. Okay, so f is bounded on closed interval AB means there exists some positive number m such that mod f of x is less than or equal to m. So this is according to the definition of boundedness. Okay, and this is for all x belong to closed interval AB because f is bounded on closed interval AB. So it means mod fx less than or equal to m for all x belong to closed interval AB. And name this as equation 1. Okay, and let E. See, I have taken these points in the set E. Okay, I have taken these points in the set and I have named that set as E. So let E equal to x1 dash, x2 dash, etc. up to xp dash be a finite set. Therefore, we can cover E by finite number of closed intervals. Okay, so we can cover E by finite number of closed intervals uj comma vj. See here, here I will show you how your uj vj will be. This is uj, this is vj. Like this is u1, this is v1, and this is u2, this is v2, this is up, and this is vp. See, I am choosing very small interval so that it covers x1. Okay, so here we can cover in such way, we can cover E, the whole set E, by finite number of closed intervals uj comma vj, where j is from 1 2 3 etc. up to p. Okay, so now that is xj dash, that is x1 dash, x2 dash, etc. up to xp dash. So I have taken that as j in general. Okay, so xj dash belong to closed interval uj comma vj subset of, see here, each and every closed interval is a subset of this closed interval a comma b. So here that we are telling, see, xj dash belong to uj comma vj means x1 dash belong to u1 comma v1, x2 dash belong to u2 comma v2. So I have named it accordingly. See here, x1 dash belong to u1 comma v1 closed interval, x2 dash belong to closed interval u2 comma v2, and etc. Okay, so this is how it is. And xj dash belong to uj comma vj closed interval, which is a subset of a comma b, and we are choosing this interval such that the summation of alpha vj minus alpha uj will be less than epsilon. So we are choosing such a small interval. Okay, so such a small interval such that even if we take the summation of all alpha, all delta alphas, that will be less than epsilon. Okay, we are taking such type of intervals. So name this as equation 2. Now what we'll do? Now removing these segments uj comma vj. So I am now removing this open interval uj comma vj, that is in that a comma b. I am removing these types of open intervals uj comma vj where the discontinuous points xj's occur. See, this actually occur in this interval. So I am removing that interval itself from closed interval a comma b. Then the remaining set will look like closed interval a comma b minus u1 comma v1, u2 comma v2, u3 comma v3, etc. up to up comma vp. See here what I am doing is here, see here, this is the closed interval a comma b. This is the closed interval a comma b. Here what I am removing this small intervals u1 v1, u2 v2. See, because of this only f is discontinuous. Okay, so what I'll do, I will remove this intervals, this small intervals where this f is discontinuous at. Okay, so here what I will do, see here, now removing these segments uj comma vj where the discontinuous points xj's occur. So I am removing these from closed interval AB. Then the remaining set will look like k equal to, so I am removing this, so I am subtracting this open interval from closed interval a comma b, and that will be like k equal to a comma u1 closed interval union v1 comma u2. See, here it is. See, after removing, I have closed interval a comma u1, and after removing this open interval, I have closed interval v1 comma u2, and after removing this open interval u2 v2, I have closed interval v2, and next closed interval u3, and etc. It continues. Okay, so this is how your k looks like. So it is union vp comma last, that is last point, that is b. So vp comma b. Okay, see here all the intervals are closed, and since finite union of closed set is closed, it implies k is closed, which implies k is bounded. Why? Because see here, we have already given that f is bounded on closed interval AB. Then obviously the part of it, k is a part of closed interval AB. Then obviously even that is bounded. And since k is closed and k is bounded, then it will be compact. Okay, so k is compact. And since f is continuous on k, okay, why? Because we have removed all points of discontinuity. Where f is discontinuous, we have removed such points, and not only points, we have removed the small intervals containing those points. So obviously now f is continuous on k. Okay, and f is uniformly continuous on k. Why? Because k is compact, so obviously f is uniformly continuous on k. See, here I have given the reason. Since every continuous function defined on closed interval is uniformly continuous on that interval, we have, see here, I have f is continuous on closed interval k. So obviously f is uniformly continuous on k. Okay, so now I use the definition of uniform continuity. Therefore, for given epsilon positive, there exists delta positive such that mod fx minus ft less than epsilon whenever s minus t less than delta, and this holds for all st belong to k, then only we tell that it is uniformly continuous. Means it holds for each and every point belonging to k. Okay, and now we construct a partition p which follows these things. Okay, so now construct a partition p which contains a equal to x naught, x1, etc. up to xi, etc. up to xn, which is equal to b, such that each uj occurs in p. So we have actually constructed that intervals uj comma vj. Okay, and j running from 1 to p. So here what we are doing, we are taking care that uj is contained in this p. Okay, vj is contained in this p. So each uj occurs in p. Second condition, each vj occurs in p. And third one, xi will not belong to this open interval. See here, this open interval is very small. This uj comma vj for all j, it is very small. And we are not taking any element in between these two. Okay, see here we are not choosing any xi's in between this interval. Okay, so what they are telling, xi doesn't belong to uj comma vj for all I comma j. So whichever I you take here and whichever j you take here, this xi's will not belong to this small open intervals. So this is the meaning of that. And the last one is delta xi is less than delta where xi is not equal to uj and xy not equal to vj. Means, see here, the difference between the two consecutive points is less than delta whenever you choose xi other than uj and vj. So whenever you choose the point xi, that is this point, whenever you are choosing this point apart from this uj and vj, then the difference between the consecutive points will be less than delta. So that is what they are telling, and I am naming this as 4. Okay, and since f is bounded on closed interval ab, we have 1 implies 1. What is 1 actually? See, this is 1. See, since f is bounded, mod fx is less than or equal to m. So actually this is 1. So I am using that now. Okay, see here, 1 implies minus m less than or equal to fx less than or equal to m for all x belong to closed interval ab. And here, since this fx is bounded, like fx lies in between minus m and capital M, for all x belong to closed interval ab, then obviously its infimum and supremum also lies between minus m and capital M. Okay, and this is for all I. Okay, so why? It is because of this reason. See, this fx is lying between this and this for all x belonging to AB. So its infimum and its supremum also lies between this for all elements for each interval. Okay, for each subinterval. See here, this x0, x1, x1, x2. So for each such subinterval, this holds. Okay, see here it's given where mi equal to infimum of f of x and capital Mi equal to supremum of f of x. And see here, this actually implies, see here, minus m less than or equal to small mi less than or equal to capital Mi less than or equal to m implies, see here, if I bring this small mi this side, then capital Mi minus small mi will be less than or equal to m plus m, that is 2m. And obviously, since mi is less than or equal to capital Mi, the difference will be greater than or equal to 0. So that is what I have written here. See, 0 less than or equal to mi minus mi less than or equal to 2m for all I. And I am naming this as 5. See, and from 4, what we have taken 4 as? See here, actually the 4 is this. Delta xi is less than delta where xi is not equal to uj vj. So apart from these uj vj, any xi, any consecutive, any xi chosen from this partition p will have their difference with the consecutive points less than delta. Okay, so that is the condition. So here 4 implies delta xi is less than delta for xi not equal to uj, xi not equal to vj. See here, this is for all I. This mi minus mi is less than or equal to 2m for all I. This is for all I. And here I'm just trying to make the difference between that. See here, this mi minus mi is less than epsilon, and this mi minus mi is less than or equal to 2m. Okay, see, whenever this xi is not equal to uj or not equal to vj, this is the condition. So whenever if it is equal, see, if I take xi equal to uj, xi equal to vj, then the condition is this. So I just want to draw here two conditions. Okay, so for x not equal to uj vj, this is the condition, and for x equal to uj vj, this is the condition. Okay, and see here how we got this mi minus mi less than epsilon for this is, see here, xi minus 1 less than delta. See, actually this less than delta implies this consecutive points less than delta. Okay, so from 3, see what is 3 actually? See, from the definition of uniform continuity, we have whenever this is less than delta, whenever these two is less than delta, then the value between their images is less than epsilon. So, whenever the difference between 2 points is less than delta, then the difference between their images is less than epsilon for all S3 belong to K. So, I am using this here. See here, this here they have given these two, the difference between these two is less than delta. Then obviously from 3 we have the difference between their images is less than epsilon, and this is for all I. Okay, that implies, since this holds for all I, because we are using the definition of uniform continuity, this holds for all I. And since this holds for all I, then obviously the difference between capital Mi and small mi is less than epsilon, right? See here, f of xi minus f of xi minus 1 mod of this is less than epsilon means, and this holds for all I means, obviously this holds for this also, because at some point f of xi will be mi, and for some point f of xi will be small mi. So the difference between these two is also less than epsilon. Okay, this means that. And now what we need to prove actually we need to prove f belongs to R of alpha, or f is Riemann-Stieltjes integrable. And from the previous theorem we have, if see, for that to prove, it is sufficient for us to prove that the difference between upper sum and lower sum is less than epsilon. So we will consider this difference now. U of p comma f comma alpha minus L of p comma f comma alpha. So here, by the definition of upper sum and lower sum, I can write like this. So this is according to the definition of upper sum and lower sum. And now here in these two summation, I will take delta alpha I common. So if I take that mi minus small mi into delta alpha I, I'll get this. Okay. So here I am splitting this single summation into two summation. One where xi equals ujvj. Here this summation where xi not equals ujvj. Okay, so here actually I have two conditions for this mi minus small mi. See, this will be less than or equal to 2m for all I, where xi equals ujvj, and this is less than epsilon, where this is not equal to ujvj. So I will use that now. Okay, so now if I use that, that will be less than or equal to 2m, and this remains as it is, and this will be less than epsilon, and this remains as it is. So here this is less than 2m, and this summation delta alpha I, when xi equal to uj, xi equal to vj, See, from 2 we have this one. See here, summation. See, we have chosen such small intervals such that the summation of alpha, the summation of delta alpha i's will be less than epsilon. So this, see, this 2m has nothing to do with this summation. If I take out, I have 2m into summation delta alpha I. And for this condition, I have 2m into delta, 2m into summation delta alpha I is less than epsilon. So now this becomes strictly less than epsilon. 2m into epsilon. And this also has nothing to do with the summation, so it will come out. And summation delta alpha I is alpha b minus alpha a. So see how is this? It will, see, if you keep on expanding the summation, no, each and every term will get cancelled, and at last you will get alpha b minus alpha a. Okay, see, I have done this previously. You can look my previous videos for this. Okay, epsilon alpha b minus alpha a. And what I'll do, I'll name this complete thing as epsilon star, because see here, this term is positive, because since alpha is monotonically increasing, obviously this will be positive. And here epsilon is positive. Okay, and here m is also positive, because we have taken mod fx less than or equal to m. So obviously this will be positive. So I am naming this entire thing as epsilon star. And since this difference is less than epsilon star, we have f belongs to R of alpha by the condition of integrability. Okay. Thank you.